Hey physicists, we're looking at components in series and parallel. It's PhySLU5 today. Sort of the beginnings of building circuits on your own. And most circuits are a combination of both of these. Maybe you've seen these in general science, maybe not, but the most basic set of components in conjunction with each other is in series, which the current sort of flows, if you're talking conventional current, through maybe like two switches and then through a load. In this case, this is a light bulb, and then back to the other side. Alternately, you could have it, and these two switches, like the current has to go through one and then the other to make the circuit a closed loop. Alternately, parallel, it could go through one loop or the other. They're in parallel, and we'll talk about the benefits of each one, drawbacks of each one. But you could think about series as maybe like a safety switch on a brake on a car. You want to turn the engine over with the key that runs power from the battery to the starter motor. But as a safety switch on the brake at the foot pedal, there's a little switch that can sense if you've depressed the brake, because you don't want the car to turn over with the brake not pressed. So you want this switch to be closed and also this switch to be closed. We want both of these closed before power will flow, before current will flow all the way through and start the motor. So that's a good example of when you might use a series. Another might be a doorbell. If you have a front door and a back door, and you have this simplified, you wouldn't use a 12-volt battery, but you have power. You want either this or this, the front door or the back door, to work for you to sound this buzzer. But it doesn't matter which one, so you either want to press the buzzer and have the button and have current flow through here, or if somebody's at the back door, they press this button. I don't want somebody to have to be at the front door and the back door to be able to do both. Oh, sorry, I'm kind of dark here. It's kind of dark. So there's some parallel and series ideas. So combinations of the components, we can run them in a couple of different ways. Here's series, here's parallel, but this is how we might show a set of resistors in series or a set of resistors in parallel. Here the switches are in parallel, or the switches are in series. And this is sort of how you might be able to visualize resistors in parallel or series. Here the battery is sort of bringing the charges up to higher potential. Potential I sort of think about as the potential energy of them. If you're thinking about this as water molecules, how high above the ground they are, the higher they are, the more gravitational potential. Here it's electrical potential, and there are different reasons for that, but in a parallel circuit, the current splits and goes down two resistors and then comes back together and out. Same thing here, you'd have current splitting, half going down here, half going down there, provided that they're the same resistance. It's not always perfectly half. But in a series, and each one of these has the same drop height, right? It has the same potential difference here and here. But you get half the current going through here, half the current going through here. Series circuit, you get the same increase in potential energy if you have the same battery, but here there's two different resistors. There's one that's dropping this much and one that's dropping this much, and overall this and this added up should be the same as this drop, where here this is the same drop as the battery EMF, this is the same drop as the battery EMF. Here you have all of the flow going through this resistor and also this resistor. So I sort of think about it as a current flowing through a series of tubes that narrow and constrict. There are some drawbacks to that, but we'll talk about those. All right. So you could think about this as well. Here's a series circuit, and if they're both switches are open, you don't get current flowing. If one switch is open, you don't get current flowing. You need to have both switches closed for current to flow. In a parallel, you need only one, right? Current here, is stopped. It can't go through this junction, so the bulb light doesn't light up. But here it can go through this side because it's a closed circuit, or through here. And if they're both closed, it can go through both, and that's fine, right? I think you've played with those before. There's a FET, if you are interested. There's a FET simulator. You can type in FET circuit construction kit, and this will kind of, you can put in batteries and bulbs and just see what'll happen when you put different batteries and bulbs and resistors in parallel or series. So here, this is a series circuit where the bulbs are in series, so the current has to go through both. You can mess with it and see what happens when you put them in parallel. All right. If you have resistors in series, it means that the potential drops a certain amount, and then later another amount, and then this voltage drop and this voltage drop, potential drop, should sum up to a total. And you can consider this whole thing, instead of two different resistors, you can consider it as one resistor. So you could take these two resistors and calculate how much total resistance, and so you just sum up the two drops, voltage drops across there. So you can try that out with this. So what's the total resistance of a 4 ohm and an 8 ohm? We're trying to put current through there. It feels this much resistance and then that much resistance. Well, the total resistance is the two resistances summed together, so 12 ohms of resistance. That makes sense to me because there's a drop on each one. There's a potential drop here, there's a potential drop here, so in total the resistances can be thought to be the same. All right, sometimes they're in parallel, and so if you have current going into this and it was split between whatever, two light bulbs or something, it would, and if these were the same resistance, you would split the current evenly, and then the current comes back together and is reformed and comes out. And one of the big ideas is that this current and this current, when they get back together, should be the same amount. So if you have like 12 liters of water flowing per minute here, and it breaks, regardless of how it breaks up, when it comes back together, you'll still have 12 liters per hour flowing out. Right, so you can kind of think about it as water. There are some inconsistencies with that, but it's sort of like saying if you have a narrow staircase where you can send some people per minute and a larger staircase where you can send more people per minute, you could put those two together and consider it with the sum of those two. So you can think about these as one resistor also. We say like the current flow I through here, the number of people moving through here and the number of people moving through there should be summative, right? Here they can be added up. The number of people walking down there, the number of people walking down there, you can add them up. Since we've been talking about current is V over R, it's like how much pressure, the current depends on the pressure and the resistance. So we're substituting this in for each of these I's, and then you can get 1 over R is 1 over the first resistance plus 1 over the second resistance, and this is sort of one of the equations that we're going to use often to make calculations about how much current flows. So try that out. What's the total resistance? Here's a 4 and an 8, but now they're in parallel. Find me the total. Like if we ignored this whole thing and tried to think about it as one resistor, sort of consolidate these, what would that resistance be? Well, we'd use that new 1 over R is 1 over R1 plus 1 over R2. We know each of those R's is 4 and 8 respectively, and then you have to have common denominators and all that stuff, and so you end up with 3/8 is 1 over R, and this is the part that I often forget to do, is flip this over, right? You're not looking for 1 over R, you're looking for R itself. So take the reciprocal, so 8/3. All right, last one. So now we've got two 8 ohms in parallel. They want to find the, let's see, what's the total resistance if they're in parallel. So I think they did this because essentially they're doubling this one. Same diagram. This one, it has the same resistance on top, but the 4 has been changed to an 8. And so we can do the same thing and calculate the resistance as 1 over 8 and 1 over 8. So you get 2 eighths, you flip it over, it becomes 8 over 2, so this has become 4 ohms. So this was 8/3, and so we've, let's see, this is a larger resistance, sorry, smaller resistance. To this one because we've added a little bit now, but it doesn't double. It hasn't like doubled this because we still have that second branch flowing through there. Cool. Take that and try these 23 through 26. We want to calculate the overall resistance for these circuits, see what you can do with them. These are pretty straightforward, and then these become a little more complicated. Cool.